Jake Nelson, and this is my presentation on Lab 1 constant velocity. So for our table of contents, we have an introduction, a slide about Newton's second law, the procedure, data analysis, possible errors, conclusion, and then further questions. So for an introduction, the purpose of this lab is to draw a comparison between an object's position when moving at constant velocity. This was done by comparing an observed change in position and a predicted change in position. We found an observed change of position of a rolling pin by using a software called Tracker, while we found a predicted change of position using a glow script computational model. And for this lab, the system we were examining was the pin that was rolling, while the surroundings was everything else, including the table that it was rolling on, the ruler, Earth, because of the force of gravity, and everything else. So for Newton's second law is also known as the momentum principle, and it relates a net force on an object to its change of momentum over the time interval the force occurred in. So as we can see, F net times delta t is equal to the final momentum minus the initial momentum. So we can rearrange that and get F net is equal to the final momentum minus the initial momentum over time, or F net is just equal to dp over dt. So Newton's second law then leads to the velocity update formula, which allows you to update an object's velocity based on a net force and a time period. And then for the procedure, the first thing we did was record a video of a pin rolling at a constant speed. Then we imported the video into Tracker and tracked the position of the pin frame by frame. And then we created a computational model in GlowScript to predict the pin's motion. Then we created a spreadsheet with observed and predicted positions and graphed them. And then we made conclusions. So for analysis for Tracker, which was the observed position, the total time that elapsed was about a second, and then the initial position was 1.67 times e to the negative 2, so times 10 to the negative 2, 0, 0. And then the initial velocity was 0.209 meters per second. And then these values were used in the computational model to help model the motion of the pin at constant velocity. And then on the right, you can see the time and position for each little step that the pin took. And then for the computational model, this was the code we wrote in GlowScript to model the motion of the pin with a constant velocity. So as you can see, the net force is 0, so the pin rolls at constant velocity. And then here's the graph comparing the two models. So as you can see with the red, which was the observed motion, it's not like a constant straight line, because there were forces that were acting on it that caused it to not be moving at a perfect constant velocity. And then the model assumed that there was no net force, and that's why there's a straight line. And then for any possible errors, one again is unaccounted for forces. So the pin experienced both the force of friction and air resistance, and while these were not accounted for in the model, they would have caused the pin to not roll at a perfectly constant velocity. And then second of all, we have human error when using Tracker. So part of the tracking software is that you have to model, you have to click on the center of mass of the pin and keep that the same for each frame. And while using Tracker, it's very possible that I did not click on the center or the same point every single time, which led to small errors in the position coordinates. In the conclusion, so the computational model would have been an accurate depiction of the object's motion and constant velocity if there had been a net force of 0. However, because there was both the force of friction and air resistance that acted on the pin, there was a difference in the predicted and observed motion of the pin. And then further questions: if the positive x and negative x axes were interchanged, then the slope of the position versus time graph would become negative. And then is the net force 0? If so, how many forces were added together? Since the GlowScript model overestimated the final position, there must have been a net force that took away from the object's true motion. These two forces that weren't accounted for were friction and air resistance acting on the pin. And that's everything I have, so thank you for listening.